Okay, let's start. So if you recall last time where we stopped is we just defined these kind of strange functions or Turing machines. So just to remind you, we had this SMN theorem. We'll see, I'm a bit lost here. Yeah, so we had this SMN theorem, which what it allowed you to do is take a Turing machine and then make a new Turing machine where it does the same thing, except one of the inputs is fixed now, instead of being a free variable, okay? So this is kind of intuitive. We saw how to do it in Python. And then the other thing, which is kind of the converse, is the universal Turing machine. So what does it do? Well, the universal Turing machine, it can simulate any other Turing machine. So it takes two inputs. The first input is the Turing machine you want to simulate. And then the second one is what you want to simulate it on, okay? So what I wanted to talk, like the last part that we need to know about this Turing machine is that this universal Turing machines, it seems at first that, okay, it can do what any other Turing machine does, but in reality, it's much more than that, okay? It's called universality for a reason, because it's really universal, okay? So what you can ask yourself is, okay, we defined this Turing machine with a head reading on a tape and whatnot, and we saw that it is at least reasonably powerful, so it is stronger than finite automata, and then we seem to be able to make many programs with it. But you could still ask the question, okay, can we make it even more powerful? Maybe we can add some extra things to it that make it compute more stuff. So for example, you have infinite examples, but you could add more tapes instead of having just a tape. It has several tapes and it can write on them in parallel. Maybe this allows you to do more programs. You can also add the possibility to stay at current location, because as we've defined it currently, you always write and then move to the left or the right. You could also tell him, okay, write and then stay where you are. You could add more general movement. So you could allow it to first decide to move 10 to the left instead of just one. You could give him the ability to generate new characters that it can use. Okay, the vocabulary is not fixed. And anything else you can think of, which is kind of physically reasonable, you can add, and you can ask yourself, okay, does this make the Turing machine more powerful? Can it compute more programs now? And okay, so if we look at these additions that I suggested, there are some that it's clear that they are not more powerful. Okay, for example, the most obvious one is this one. If we had the possibility for the head to stay at the current location instead of having to go left or right, we're not more powerful, because we can just make a Turing machine that it has a state when it goes right, it then goes back left, and this is equivalent to stay at the same location. Same thing, when we have more tapes and more heads, okay, we can do stuff in parallel, so it's faster, but in principle, our Turing machine can simulate that. It can just separate the tape in several pieces, and then write first the first one, then the second one, then the third one, and overall, it's like it's written in parallel. It will be much slower, but it will be just as powerful. Same thing for the general movement. I mean, it's clear you can have a Turing machine that does right, then right, then right, then right. It has a special state that does right 10 times in a row, and so on. Okay, then there are others which are not so clear. Maybe creating new characters allows you to do some stuff that you couldn't do before. It's kind of not that obvious that it's not more powerful. And then you can think about a lot of things. And okay, even if it's not obvious, let me see. Yeah. So some things are obviously as powerful, some things not obviously. And so people, even beyond like trying to make the Turing machine more powerful, people designed other computing paradigms, or like other ways of doing computations which are completely unrelated to Turing machines. Okay, they just designed a whole other way to think about computations that has nothing to do with Turing machines. And two famous examples, I'm sure there are more, are the following. So first it was Gödel, which introduced the notion of partial recursive functions. And these are all the functions that are closed under composition, recursion, and minimization. Okay, you don't need to know the details of this, but there are some operations that you can do whenever you have a function or two functions. And then, and you force it to contain at least the zero function. It's just a function which is constant, gives zero for any input. The successor, this is a function that adds one to the input. And the projection, this is kind of the function that ignores some amount of inputs. So introduce these partial recursive functions, which is just a class of functions. And you notice that using this, you can define a lot of functions. I mean, this class contains a whole bunch of functions which you can think of as programs. Like one of these functions is a program. It has an input and an output, and you can use a function to compute some stuff. So a completely different way of doing computations, having these strange functions. Then the other thing was from Alonzo Church, which creates something called lambda calculus. And again, it's just a set of expressions. You don't even have a function here. You just have some expressions. And they are defined by induction. Okay, just to give you an overview. So a valid lambda expression can be just a variable that you give a name. Then if M is already a lambda expression, so is this thing. Okay. When you define lambda calculus, you don't say what this is, but the interpretation that you give it afterwards is that this is the function that given X does M. Okay. So for example, this expression here means the function that takes X as input and outputs X plus 1. You interpret it like that. Okay. And then you have other rules. Okay, if M and N are lambda expression, then this is also a lambda expression. And this means apply the function M to N, okay, when you interpret it. And then you have some rules on how to compute with this. So given a lambda expression, you can do some operations that simplify it. And okay, this is super abstract. At the beginning, when I read about this, I really didn't understand how you compute with this, because at the beginning, you just have some text. You have some rules on this text. And it turns out that with this, you can start to say, okay, I define the zero as I don't remember even if it's the empty set or something, but then you define something as zero, and then you say, when I apply a function to this gives me the 1. When I apply it twice, this gives me the 2, and then you kind of define the natural numbers, and then you can use those to define the sum, etc. Anyway, if you've used functional programming, it's kind of inspired from lambda calculus. I'm not very knowledgeable about this stuff, but suffice to say that Alonzo Church designed this thing, and he noticed that with this definition, he can also do a lot of computations. Like he can prove that you can make programs that recognize regular languages and more, etc. And so it was very strange because you have all these different, let's say, way of computing stuff, and they seem to be kind of just as powerful as one another. So people are saying, okay, no, you need to study an algorithm, you need to study the Turing machine, or no, actually you need to study lambda calculus. And what's super nice is that ultimately, you don't have to choose what kind of algorithms. Do you use lambda calculus? Do you use partial recursive function? Do you use Turing machines? Ultimately, people have shown, I don't remember who shown, I think probably Turing or Church shown the equivalent. They shown that all these kind of ways of doing computations are completely equivalent, okay? And to show this is relatively straightforward. All you have to do is show that Turing machines can implement lambda calculus and vice versa. You can implement a Turing machine in lambda calculus. And if that's the case, it means that they're perfectly equivalent. So any function that is computable by a Turing machine is also for lambda calculus and for Gödel, the Gödel's partial recursive functions. So that's kind of crazy. Okay, intuitively, you would not expect these very different ways of doing computation to match exactly in what they can compute, right? So these systems have nothing in common, and yet they are completely equivalent, it seems. And so people noticed this thing already. It was kind of strange that it perfectly matched like this. And then they started, okay, I don't know, I'm kind of inventing stuff, but that's kind of my idea of what happened. They started trying other computation definitions which were large enough, and they kept saying, okay, this is again equivalent to Turing machines. This new thing is equivalent to Turing machines. And so in the end, you kind of have to conclude that no matter what you can come up to compute stuff, so long as you're sufficiently powerful, so for example, finite automata, they're not powerful enough, but so long as you're sufficiently powerful, you end up being able to compute exactly what a Turing machine can compute, okay? And now you have to put some caveats. I mean, this is true as long as you don't give your computing way some unphysical abilities. Like, for example, you cannot allow your Turing machine or your whatever machine to do an infinite number of steps in a finite amount of time, right? Or you cannot allow it to manipulate real numbers exactly, like the exact representation of the real number with all the numbers. So it cannot be infinitely precise, for example. And so, yeah, as long as you don't do this crazy stuff, it seems to always end up with the same computational power. And that's kind of nice because it kind of relates a little bit computer science to physics. Okay, what is reasonable physically to be able to construct as a machine cannot be more powerful than a Turing machine. Okay, so this kind of idea is called the Church-Turing thesis, and it's super important. And it says, to summarize, a function on the natural numbers can be calculated. So by an effective method, by that I mean a function of the natural number is computable if and only if it is computable by a Turing machine. So in other words, I don't care about what did you come up with to do computations. If it's powerful enough, I can just look, is it computable by a Turing machine? No, then it won't be computable in your strange way of computing functions. And so also what this means is that it makes sense to talk about what algorithms exist. Because the notion of algorithm, although you need some kind of computational schema to define it precisely, we've shown that any computational schema that you can come up with will be exactly equivalent. Okay, so we can actually say this problem here is non-computable. And it means it's not computable for any of the equivalent computational schema you can come up with. All right. So any questions about this universality, Church-Turing thesis? Okay, if we did not have that, we'll be in trouble because each time you want to speak about the existence of an algorithm, you would also have to specify, okay, but in what language are you doing this algorithm? Here, thankfully, we don't have to do that. We can just speak it completely broadly. And that also means that when we'll do these theorems about the existence of self-reproduction, we know that it's applicable to a broad range of cellular automata, programming languages, etc. We are not showing it just for a very narrow thing. So that's why I have to present this thing, even though it's not really artificial life directly. Thanks to this, we can actually talk about self-reproduction for most things. Okay? So this result, it cannot really be proven just because this effective method definition is kind of not precise. But yes, so as we said, it means that what you can do in C++, you can do in Python, you can do in C, you can do in assembly, you can do with a Turing machine, okay? And so now the Turing completeness kind of take on a new meaning. So we say that a programming language or a way to do computation is Turing complete if it can simulate any Turing machine, okay? And it's equivalent to say it can simulate a universal Turing machine. So we know whenever a language is Turing complete, we are happy we can do anything we would do with any other language. It could be less strong, it cannot be stronger, except if it has these unphysical abilities. Okay. Now that we know that we can define algorithm independently of the way you compute this algorithm, let's look at the limits of Turing machines, okay? Whether there are functions that they cannot compute. And then we'll be done with the Turing machines. So what is an example of a non-computable function? Okay, so let me just do a small reminder on the languages. So there is a small difference when you try. So remember, for DFAs, we tested their power by which languages they can recognize or not. Okay. So for Turing machine, we'll do the same. We just have to add one extra thing because the Turing machine can go into a loop, whereas the DFA always terminates, right? So we do not have a single definition, we have two. So the first one is a language is Turing recognizable if and only if there is a Turing machine that accepts each string whenever it's in the language. Okay, so in other words, you give me a language, which is a bunch of strings. It is Turing recognizable if I can do a Turing machine that whenever you give it a string, it says accept. And if it's a string which is not from the language, then you don't expect anything. It will either refuse or loop. Both are valid. And then you have the stronger constraint, which is Turing decidable. And that is a language is Turing decidable if the Turing machine which accepts whenever it's given a string from the language and rejects otherwise. Okay. So the difference between the two is that to recognize the language, you can also loop whenever it's not a good string. Whereas to decide a language, you need to always either accept or reject. You're not allowed to go into an infinite loop. And this is much stronger than this, obviously, because here you have to be sure that your program finishes. Okay. So clearly, as we said, the regular languages, so the languages that can be recognized by a DFA, they are also Turing decidable because the Turing machine has, in particular, a finite automaton in its definition. So we can just use the finite automaton part from the Turing machine to decide it. So we must go beyond that and find some examples. So here we'll just show one example, which is essentially the quintessential example of the non-computable function. And more or less, every other time you find a function which is non-computable, to prove it, you kind of connect it to this example, from what I know at least. So we consider this language here, LTM, which is composed of two, let's say, strings or numbers, M and W. So this is kind of the string that we get as input, where M is a description of a Turing machine, and W is a string, or the input of the Turing machine, okay? So this language contains all the pairs of Turing machines with the strings that they accept, okay? So in other words, to explain it a bit more in English, so give me a program and an input, so M and W, and I have to tell you whether the program M will return true. So I kind of have to predict what the program M will do to be able to decide this language, okay? So first, let's show, it's very easy to show, that this language here is Turing recognizable, okay, not decidable. So all we have to do is, given M and W, we have to say yes if M of W say yes. So we have to accept if M of W accepts and reject or loop otherwise. Okay? So that's kind of easy, right? It's almost, the answer is almost contained in this definition, okay? So what we do is we will use a universal Turing machine, or at least a Turing machine that can simulate other Turing machine. And this will be our machine that recognizes a language. So this machine, given this tuple of inputs, what it does is just it actually runs the machine M of W, okay? It can do that because it is a universal Turing machine, so it can run other machines. And so if M of W returns true, then the Turing machine also returns true, okay? And otherwise, I mean, if M loops, our Turing machine will also loop since we are simulating M. And if M, yeah, I guess I have to add, if M of W refuses, the TM or RTM refuses as well, okay? So you can see that we do not decide this language TM, but we do recognize it, okay? Whenever M of W accept, we will also accept. So we accept exactly for all the languages that are in there. All the strings, sorry, that are in there. That's good? All right. So this language, of course, I chose it because it's recognizable, but it is not decidable, okay? It's an undecidable language or undecidable problem. And the other name for this problem that you might have heard is called the halting problem. Why is it called the halting problem? Because essentially, to be able to decide this language, we must be able to know whenever the Turing machine M will loop, right? Because the way we are recognizing it is just simulating M of W. So if we know in advance whether it will loop, we could just say, okay, we reject because M will loop. So in other words, if you know when a certain Turing machine will enter into a loop, you're also able to decide this language, right? So the argument, so if we knew how to tell when M of W loops, we could decide this language in the following way. So let me just describe it. So we have our TMH, let's call it H, okay? Given M and W, first check if M of W loops. If yes, then reject. Okay, if it loops, it means that it won't accept, so we have to reject. If it doesn't loop, just simulate M of W and accept if it does, reject if it doesn't. Okay, so this hypothetical Turing machine H will decide the language because it will say exactly yes whenever MW is in the language and exactly no whenever it's not. Okay, but actually this H cannot exist, and the proof is kind of nice, kind of similar to the self-reproduction proof. So these proofs, if it's the first time you see them, it kind of can be kind of a mindfuck at the beginning. If you read it over a few times, you should kind of understand actually what's happening. But let me just show it here. So it's a proof by contradiction. Okay, so we assume that we have this Turing machine H that solves the halting problem, or in other words, that decides if a Turing machine loops or not. So yeah, H will get two inputs. First, N, the Turing machine, W, the input to the Turing machine, and it will accept if and only if the Turing machine does, and otherwise it refuses. Okay, remember phi N of W just means run the Turing machine N on W. So now we make a new Turing machine, which we call T, that takes N as an argument. Okay, what T does, it will simulate H of NN. So things are already starting to get kind of convoluted. So what does H of NN do? It simulates what the Turing machine N does on itself and tells you if it goes into a loop or not. And so what T will do is first, it will simulate H of NN. Since H decides, it always halts, okay? So this will give an answer. So H of NN will either accept or refuse. That's by assumption, okay? And then it's easy. What we do with T, if H, sorry, here should be H of NN, whoops, H of NN. So if H of NN accept, T will go into a loop. Okay, you might say, okay, how can you make T go into a loop forcefully? Well, it's very simple, right? So we have H of NN. If it accepts, we just if H of NN accepts, then we do while true, for example. Okay. If H of NN refuses, then T accepts. Okay, so this T, in kind of the way you should see it, is kind of does the opposite that the halting problem does. So instead of telling you yes when it finishes and no if it loops, it tells you the opposite. If the thing finishes, it will go into a loop. If the thing refuses, it will accept. Okay. How do we use this to make a contradiction? Again, so T depends on H. and then we will feed H this T, okay, acting on itself. So there's some double recursion. So here, don't think too bad about what is happening. Just, you know what T does, and now you're good. So we compute H of TT. So what does this mean? This means we ask the question. If I compute phi T of T, so I give the program T itself as input, what will happen? Will it loop or will it stop? Okay. I actually already wrote this. Okay. H consider phi T of T and look if it accepts or if it doesn't accept, right? And now we just have two possibilities. Either H of TT accepts, okay? What this means is that T of T should accept by definition of H. But let's see what is T of T. So T of T will evaluate H of TT by definition. But since H of TT accepts, T of T loops because it does the opposite as what H of TT says. So we have a contradiction because we assume that H of TT accepts, so which means that T of T accepts, but we show that T of T must loop by definition of T. And then on the other hand, if we assume that H of TT rejects, which means that T of T loops or rejects, if we look at what T of T actually does by the definition we gave it, it looks at H of TT, which is a reject. So T of T decides to accept, which is in contradiction with this. Okay? So H cannot exist simply because if H were to exist, we'd have a contradiction. Okay? We'd have this program T of T that both loops and accepts. So the ultimate problem is undecidable. Okay? So what I want you to notice, okay, I suggest that if you're kind of confused, it's normal. You should go through the proof again and see what's happening. But what I want to make you notice is that we have kind of this double application of a program onto itself. So T uses something of a program applied to itself, and then we apply T to itself again. And we'll see that this kind of motif will come back when we try to prove that there are programs that self-reproduce. The reason for this is not extremely clear to me, but it's kind of related. Okay, no, maybe let's not say that because it will send us to a rabbit hole. Yes?
It seems to me that it's kind of the same problem that people had with sets at the beginning, that you can define a set with some elements not belonging to that set.
Yes, yeah. So it's kind of, yeah. So the way the proof goes is very similar to that. So that's what I wanted to say. So if you know about Cantor's diagonal argument, it's kind of an expression of this, and it's the same also for the sets. So it seems that, at least from what I've read, I'm not a super expert in this, every time that you want to show some undecidability or something like that, you almost always use some sort of self-reference. In the sense, so the diagonal is kind of, they call the diagonal argument because you can see that somehow the diagonal argument is when the program eats itself, right? If you list all the programs and all the inputs on the diagonal, you have the program acting on themselves. So in both cases, it's kind of a diagonal argument. And
why can you not just prevent that? Like,
why you cannot prevent that? Well,
because for sets, you can, like, you cannot define a set through something that refers to the set itself.
Okay. Okay. So the question is, why cannot prevent this like ill-behaved behavior? So the problem is exactly that if you make your machine powerful enough, so as powerful as so your computing scheme as powerful as a Turing machine, then you will necessarily have this problem. Okay. Here we didn't assume anything beyond the fact that we have a universal Turing machine. So you can try to prevent that. For example, for finite automata, there is not this, I mean, you don't have these kind of strange programs that does this diagonal argument, but you're necessarily less powerful. So if you want to be at least as powerful as the Turing machine, you were cursed with having universal Turing machines. And so you're cursed with this contradiction. All right. So yeah, that's what I said. Notice the use of self-reference in the proofs. Most proofs of undecidabilities of problems use this kind of self-reference. If you have some example where it doesn't, I'm very interested to hear. But yeah. Okay. So the last thing is just two definitions, and then we're done with Turing machines. Okay, there was a comment from Hassan on the YouTube. I will read it later, then comment on it. Yes, so a definition. So we just say when you have a function of the natural numbers over the natural numbers, we say that this function is computable if there is a Turing machine that essentially implements this function, okay? So the Turing machine eats X and it outputs, we have to define what is an output, but you have many ways of doing that, but that's fine, is f of X, okay? So by this meaning, if I want, yeah. And if this function, so this function does not have to be defined on all natural numbers, but if it is, then it is a total computable function. Otherwise, it's a partial computable function, okay? So when f is not defined on the input, what this becomes in the implementation of the Turing machine is the Turing machine loops, okay? It's not defined. So, for example, if we take this function here, which gives 0, so 1 if the Turing machine halts, and 0 if it does not halt. So this function is kind of the solution, a solution to the halting problem. You can define it, of course, but this function is not computable. Okay, you cannot design a Turing machine that implements this function because of what we mentioned. So if we have this other function here, which is very similar, it's just 1 if the Turing machine halts and undefined otherwise, this function is computable because it's just implemented by the Turing machine that recognizes the language. Okay, because we have this undefined, we're allowed to loop for some inputs, and so this is the function that recognizes the language. This is the function that decides the halting problem. Okay, so here I have a small question. It's kind of hard if you've never seen this stuff, so just answer from like your intuition. So the question is, this function h bar, it's very similar to the function f, but it does kind of the opposite. So it tells you whenever the Turing machine loops, and otherwise it's undefined. So the question is this function computable or not? So just go with your hunch. There is a way to prove it, kind of not too hard, but if you've never seen this kind of stuff, it's quite hard. The Slido code is here. Is it really legible? Yeah. Okay. I just want to see the intuition of people that they have on this problem, if they haven't come across it. Okay, we have a few answers coming in. Most people saying no. It's kind of interesting because it's very similar to this one. This one we know it's computable. And this one is very similar, so. Okay, let me wait until I have 10 people and then I'll show. Okay, so we have 18% of yes and 82% of two. So, okay, people have the correct intuition, or people have already seen that. That's also a possibility. At least people know that there is an answer to this. And so, okay, the answer is indeed no. And why is it no? Okay, does somebody want to say why it's no? Somebody has an idea? Yes?
If it was computable, then we'd have a Turing machine compute it, and then for the halting problem, we could use it to say, well, if this Turing machine returns 1, then we
okay. Yeah, very good. So that's correct. So the function h bar is not computable. Okay, so it's equivalent to say that the language n loops is not recognizable. And why is that? The problem with that is that if we had h bar, we can show that we would be able to solve the halting problem, decide the halting problem. Sorry. Okay. So how to see this? Well, so if we have h bar which is computable, then we have n of h bar, which is the corresponding Turing machine. And consider also the other Turing machine nh, which recognizes the halting problem. Okay, so it implements this function here. So what do we do? So we have nh that accepts if x halts, and nh bar accept if x loops. So all we have to do is make a new Turing machine that would simulate in parallel, or like one after another, not first nh and then nh bar, but both together. It simulates nh and nh bar on its input x. But we know that either nh will halt or nh bar will halt, but necessarily one of the two will halt. And so what we'll do is just that, okay, if the one that halts is nh, then we know that x halts, so we can accept. If the one that accepts is nh bar, then we know we should refuse because the thing loops. And so we decide we have solved the halting problem, okay? So this is impossible because we have shown that we cannot decide the halting problem. So we must conclude that h bar is not computable, computable. So in other words, this language is not recognizable, okay? And so this is kind of a proof of a more general theorem. So if you have a language and its complement that are both recognizable, then you can, then the language is also the languages are also decidable, okay? And the last thing I want to say, so the intuition for why this language is not recognizable is essentially because how do you know that a Turing machine will loop? It's very hard to know. Essentially, to know it loop, you have to know that it doesn't halt. So you would have to kind of simulate it until you hope it halts. But of course, if it loops, you will keep simulating forever. So we'll never be able to say that it loops for certain. So yeah. Okay, so next time self-reproduction, but it's actually today. Are there any questions at the end of this Turing machines? So I repeat, if you are confused about these proofs, it's perfectly normal. They take some thinking to actually get convinced. All right. So course number 4 is self-reproduction and quines. Okay, so we'll actually put to work all the things we've learned about the Turing machines. Okay. And today I also wanted to say, because about the project, just so now I guess that people that are here still today will probably go until the end of the course. So I'll let you know soon about some details. People ask me if they can do the project in a group. Yes, there is no problem about that. You can do either alone or in a group, as you prefer. Would say maybe max a group of 3 people, but okay, if you really want to do it with 4 people, it's fine for me. And think about it if you have something. Also, I will put on the website some kind of preliminary program for the next lectures, which will probably change, but at least it gives you an idea of what to expect for the next courses. And I will give you more details on the projects, but kind of start thinking about it if you have an idea. And remember, it should not take you like full time for 3 weeks, right? It should be a small project, takes you like 10 hours to set up, and Okay. So reproduction for Turing machines. So what we saw is that the Turing machine is a nice model to study, like any other computational model, because of the Church-Turing thesis. The Turing machine is kind of nicer because it's much more palpable than, say, lambda calculus or the Gödel's recursing functions. Okay, you can actually kind of imagine how the Turing machine will work, and it's very close to how computer works, or people have a better intuition for it. And so from now on, we'll really talk about Turing machines, but keep in mind that everything we show for Turing machines holds for any Turing complete language or system, okay? And what we want to show is that whenever you have something as powerful as Turing machines, you necessarily have some self-reproducing programs. And so that's where we come really back to A-life, because it seems that this reproduction, the fact that we are able to reproduce, that reproduction is actually possible, it's kind of surprisingly linked to computer science and computability of functions. So first, before showing that we have self-reproducing Turing machines, we need to define what do we mean by self-reproduction for Turing machines. And okay, this is something I kind of come up with. I never seen somebody talking about this before, but it's very important because we'll see especially for A-Life. Okay, if you're interested in making programs that print their own code, it's not very important. But for A-Life, we'll see that it's kind of important to really understand what we mean by self-reproduction. Okay. So by definition, recall that a Turing machine is simply a collection of some information, okay? It's a collection of its finite set of state and the transition function that describes how it acts on the tape. So all a Turing machine can do is act on the tape. Like we've designed this way, all it can do, it can like move on the tape, it can compute some stuff, but at the end of the day, from the outside, you just see it acting on the tape. It has no way of constructing a new finite automaton or new states or a new tape reader. I mean, these are not even defined, right? So we cannot really define self-reproduction naively for a Turing machine because a Turing machine can just write stuff on a tape. So it cannot make another Turing machine, right? In real life, if we had a computer that actually does stuff on a tape, you might imagine that with the tape, it might be able to kind of fold the tape such that it makes another processor, I don't know. But for the Turing machine that we mentioned, all it can do is act on a tape, so it cannot reproduce in the naive. It cannot make another Turing machine. So yeah, we'll need to be a bit more abstract to define for Turing machines, okay? And yeah, so here's just a comment that when we talk about Turing machines, we kind of implicitly assume that this Turing machine that we decide kind of exists somewhere and physically executes the operation that is designed to execute, right? And it's not just some string written somewhere. Okay, there's kind of this idea that you can actually put this Turing machine somewhere and let it compute. But okay. Okay, so let's start. How will we define self-reproduction for a Turing machine? So we know that we can associate an integer to each Turing machine. So we have an equivalence between integers and Turing machines. And instead of thinking about integers, you can also think about strings. Kind of when you have a program, it's defined by a string. And so these strings can describe the Turing machine, say by listing the set of states, describe precisely the transition function, and so on. So these are two ways kind of to represent a Turing machine, right? So what we call this a representation of the Turing machine. And so this representation is a choice that we make. So before we chose a representation as some integers, but we can be much more general than that. Okay, so the representation of a Turing machine could live in any kind of space. It doesn't have to be an integer. Okay, it could be text on a piece of paper. It could be some Python code that implements the Turing machine, other code, etc. So the only thing that we require from this representation is that there is a bijective map between a Turing machine and its representation. So its representation corresponds to exactly one Turing machine. And so this will write by representation of n to denote the representation of the Turing machine n. Okay, and n here can either denote the abstract Turing machine, or if n is the integer, this integer is itself a representation of the Turing machines. Okay? All right. So once you have chosen a representation of a Turing machine, we could in particular choose a representation that kind of fits on the tape of the Turing machine, right? So we can make it so a Turing machine can print or output representation n as part of its computation. And then a reasonable definition of self-reproduction is a Turing machine n self-reproduces if it outputs the representation of itself. So in particular, okay, here you see that we have this output in kind of quotes because we haven't defined what it means to output yet, but we'll come to that. So here just a note. So you know that Turing machine, they get as input some numbers usually. And so what here I want to note is that there could be several representation functions in the story. So for example, when you have the universal Turing machine, it takes as input on its tape, as an input to the Turing machine, the representation for the other Turing machine that it wants to simulate. So here we have a representation that we use to give as input, and it does not necessarily have to be the same as the representation for the output. But that's just a precision. All right, so representation, just a bijection between Turing machine and some space that we choose. So here is just for some nomenclature. We will name a self-reproducing Turing machine a quine. Okay, this quine word comes from computer science and programming. I don't remember the etymology of it.
It's the name of a philosopher.
It's the name of a philosopher. Okay, and it's given. The name quine is given to a computer programs that print their own code. Okay, so a quine is kind of a self-reproducing program, and that's what we'll call our self-reproducing Turing machines. So before we continue, we still need to define what it means to output for a Turing machine. And we'll see that it's intertwined with the choice of representation that we make. But let's make the break here and let's come back in 15 minutes. Okay, future Vasilis here. I'm just re-recording this small part of the course because during the lecture I forgot to unmute myself. So some data was without sound. So let me just redo it. So where we stopped at the break was that, okay, we defined what is a representation of a Turing machine. But then we still need to define, to be able to actually understand what self-reproduction means, we need to understand what it means to output something. And so for me, this choice of output is completely free. Okay, so the Turing machine does some stuff on its tape, and you are free to interpret what it does in any way that you want. So it's completely a matter of conventions for me, but you need to choose how you output. So here are some possibilities that you could consider. So you consider as output the contents of the tape when the Turing machine halts. So you just look at the tape when the Turing machine halts, and that is your output. That's one possibility. This is kind of very natural, but it might be a bit annoying because it could happen that, okay, when you do the tape, you also use to make computations. And so it might be a bit annoying to need to erase all the computation that you did to then place the output. So one solution that you could say, okay, let's consider as output only the odd locations in the tape and ignore the even locations. And that way you can do your computation on the even locations, and you have the odd locations to write whatever you want to output. Or another possibility is to consider as output all the parts of the tape that are surrounded by double quotes. Okay, so if I write double quote something double quote, this counts as output. That's another possibility. And yet another one, which is much more convoluted, but still valid according to my definition, which is extremely loose. You use the contents of the tape when the Turing machine halts, and you interpret them as C++ code. You then execute the C++ code and look at the output in the console, and that's the output of your Turing machine. Okay, so that's much more convoluted, but still valid. So in all these cases, the output that we choose is represented, it lives in the world of strings, but you don't have to limit yourself to that, right? You could also define as output, okay, when the Turing machine halts, the content of the tape as a string is encoded into a QR code, and this is the output. It's the QR code. So in that case, the output lives in the space of images, or in the space of QR codes, as you prefer. All right. So we have a lot of freedom in defining what we consider to be the output of the Turing machine. And what I will consider that every definition is valid. Okay. There, of course, will be some stranger definition than others. There are sometimes some natural definitions, But in all cases that you have, you need a way to decide how to interpret what the Turing machine does. So there is no specific reason why the output on the tape would be more valid than all the other examples that we gave here, right? In any case, you need an interpretation of what's on the tape. And so I say, okay, allow any interpretation that you wish. All right, so this is the output. You just decide on how you will consider the output. So just as a comment, so in principle, you could have some continuous output as the machine operates. But by that I mean that you don't have, for the output, you don't have to wait for the Turing machine to halt to actually have some output. Okay, this happens very often. If you have a Python program. The Python program can print some stuff on the console even if it hasn't finished operating. So you can also define all the outputs that we defined here were kind of defined, or the Turing machine outputted only when it halted, but this is not necessary. It's just, usually it's cleaner to say that you have an output only when you stop computing, but I don't think it's necessary to restrict to that. So let me here make a few more natural examples of the choice of output and representations. So as we said, for Turing machines, for the standard Turing machines, the representation of a Turing machine can be just the Turing number. So here I write it like this. It's kind of trivial, but it is what it is. And the output, the more standard one, is just the full tape content when we halt. When the Turing machine halt is the output. And you can either look at it as a string, or you can look at it as a number as well. That's up to you, depending on which characters you allow for the Turing machine and so on. So for von Neumann Turing machines, it's kind of different what is natural. So the representation of the Turing machine, in the examples that we constructed of the self-replicator, the input, the representation for the input was a physical tape of CA states, which were either empty or the downward pointing arrow. Okay, so we had this input tape to the Turing machine, used a representation which was in terms of these tape made of arrows. So that's one possible representation. Okay, but the output in this case, the representation of the input to the Turing machine and the representation of the output of the Turing machine is not the same, right? For traditional Turing machines, the input is on the tape and the output is also on the tape. Here, the input is on this physical tape of states, of von Neumann states, but the output, the most natural thing to take is to take the state of the full cellular automaton world, because the von Neumann self-replicator, or the von Neumann Turing machine, has this constructing arm, which allows it to actually modify the world around it. And so its output can be very naturally considered to be what modifications it made to the world. So in other words, the full state of the cellular automaton world can be its output. And you can have some mild variants, which are all natural. So you can count as output each execution frame of the cellular automaton. So this is, you get an output as the thing evolves. Or you can consider the output only when the Turing machine reaches the halting state. That's another possibility. And if you don't want to consider all the full state of the CA world as the output, you can say, okay, this is a region of the world where you're allowed to output, and I will consider as output only the states that lie in this region. Okay, all of these are natural. And finally, for Python programs, the representation of a Python program, the most natural is simply the code of the program. So it's a string containing the code. And the output, the most natural when you have command line programs, it's everything that is printed in the console. And if you have a graphical window, the natural output is simply the image on the graphical window. So in that case, the output is actually an image or even a video, if you want, through all the execution. And that's pretty much it. And so I go back to the present-day Vasilis for the rest of the lecture. To summarize, and for the people that unfortunately had no sound on YouTube, we have to define the representation that we did before the break, and we have to define what we mean by output. So by output, we are completely free to choose anything we want. Any space is valid, strings, images, whatever. We just need a way to decode what the Turing machine does into an output. Okay, so now we have the representations and the output, so we know what it means to actually self-reproduce. And I want just to mention one last thing before we actually go to the actual implementation of the self-reproduction, and it's kind of this notion of an abstract versus real self-reproduction. So what do I mean by that? So when we have a Turing machine, let's say we take the representation of the integer, and as output, we take the content of the tape. So a self-reproducing Turing machine, number n, is the Turing machine that when it executes, it writes the number n on the tape. Okay. Obviously, this self-reproduction feels much less real than the self-reproduction of the von Neumann self-replicator, which, what does it do? It actually goes and construct a perfect copy of itself that you can then turn on and that will itself make a copy. So it's not just an abstract representation of myself on some tape. I actually made a physical copy of myself. I have two copies of me in the physical world. So I want just to outline this difference and see why it's not a really important difference. Because you might think, okay, what I want for A life, it's certainly real self-reproductions. I don't want to output a representation of myself. I want to actually clone myself. But we'll see that it's not so different. So the reason why the Turing machine reproduction feels less real is because we have a different choice of output function. So in the case of the Turing machine, we are left with an abstract copy, whereas, the output function generates a representation, whereas for the von Neumann CA, the output is the machine itself. It's not an abstract copy, it's actually a perfect copy. In some way, there is no representation in the middle. We actually make a copy of ourselves, okay? And so that's kind of the big difference. So it seems that we have these two tiers of self-replication according to what output we choose. So in a life, as we said, we want to have the real kind of self-replication. The new copy should live in the same world as the previous one. But we'll see that if you give me a system where you have abstract replication, as I defined above, I can always design a world in which this abstract replication becomes real. And this is thanks to universality. So let's see in practice what I mean. So here I have a nice image to show you. So we consider the Turing machines, okay? For the representation, we use the Turing numbering. And for output, we choose the region of the tape enclosed with quotes, right? So consider R to be a self-replicating Turing machine. So how can we make this replication real? Because right now it's just writing representation of R on the tape. So what we do is we create a world in which the representation of R is kind of the physical form of the Turing machine. So what do we mean by that? So I think it's summarized nicely by this picture. So what do we have here? So here we have a universal Turing machine, and this is the tape of the universal Turing machine. And what we do is we design this Turing machine in this way. So the Turing machine scans the tape. It looks at all the regions that are enclosed in quotes, and it simulates the Turing machine corresponding to this number, okay? So here, for example, we put a representation of R. So the Turing machine will scan this tape and say, I found a Turing number, I should simulate it. And it will simulate it with the output being here. It designates a region where it makes the output. And so it will simulate R on this region of the tape. And so what's happening here is that we have this world, which is the tape world, in which a Turing machine and its output are both on the same level, right? The Turing machine both lives on the tape and writes on the tape by an intermediate universal Turing machine. So in a way, the Turing machine, here the universal Turing machine, is literally the universe, and you have some machines inside which can actually do a real self-replication, right? Because in this world, the Turing machine R is not outputting an abstract copy of itself. It's outputting a string, but it is itself a string. Okay? So this is one way to actually take a machine which has an abstract self-replication and then implement it in a world controlled by a universal Turing machine in which this is a real reproduction, right? So in a sense, you might think, okay, abstract self-replication is not enough. You need some kind of other thing. You need to prove that you have this constructing arm or something of the like. But in reality, no. You can always design this new world in which the abstract self-replication is real. So yeah, so this is the main difference that I want to make that I've seen mentioned anywhere. But yeah, so you have this TM world, which is actually your artificial life world, in which here you have actual agents that self-reproduce and such and such. Okay, any questions about this? All right. So now that we're happy with this, let's go on and build the self-replicating Turing machine. So we'll show two proofs. Probably the second proof will be next time if we don't have time today. So the first proof is very constructive. So you'll see exactly what is happening and how we construct this self-reproducing machine. But it is not that obvious what do we actually need to have this self-reproducing machine. What are the necessary ingredients? So afterwards, we'll make a second proof, which is completely abstract, really not really constructive, but we'll see that in this one, we can actually more easily see what are the assumptions that we make. So we have to make the choices about self-reproduction, as we said. So we construct a self-reproducing Turing machine. For the choice of representation and output, we choose the integer representation, Turing numbering. And for the output, we'll do, as I said, so the portion of the tape surrounded by quotes. So we need a last assumption, okay, which is actually quite important. So we need to assume that there exists a Turing machine P, which we'll call the print Turing machine. What does this Turing machine do? So P takes as input M, a Turing number. The output of the Turing machine is also a Turing number. And more precisely, so P of M is a Turing machine. Okay, so let me rephrase that. So you feed M to this print machine. Okay, it outputs P of M. This is just the way we write its output. And this output is also a Turing number. So it designates another Turing machine. And what does this Turing machine do? Well, it outputs M. Okay, so in other words, so P is not a program that itself prints M. It's just a program that you tell him what you want to print, and it gives you a program that prints that. Okay, so for example, I want to have a Turing machine that prints hello. Okay, so what do? I just, this Turing machine has Turing number P of hello. Okay, so this is a Turing machine, is the output of P when you feed it hello. And so if I do phi of P of hello, oops. So if I run this Turing machine here, this will output hello. Okay, that's kind of ugly, right? So yeah, so be careful because so I have two applications of Turing machine, right? I first apply the Turing machine P to the input hello, okay, and this outputs another Turing number named P of hello, and then we execute this Turing number, which outputs hello. Okay, so just to make it a bit clearer, an example in Python would be this function here. An example in Python would be the function p that at inputs takes a string s. Okay, and what it will do is return. It's kind of annoying. It will define another function, right? Because it needs to return another Turing machine. Whoops, and this function, what it does is print s, and so
you don't want to put
it return f.
You don't want to put the quotes in
Yeah, sorry. Okay. So you see, p of s gives you a new function f. When you run this function, it actually prints s, but not before. And that's what this function p does. Okay. All right. So first of all, I say that we need to actually have this print machine, and depending on which representation and which output I choose, this machine print might not exist, right? So if I choose, let's say, if the output I choose just the tape when the machine halts, and as a representation I choose like a picture of the Turing machine, obviously there is no Turing machine that outputs a picture. Okay, forget about this. You will see clearer next. But anyway, we assume that this print function exists. These are more general definitions. We don't really care about that. Let's continue. Okay, so we have this print function. And what we want to do is have a program that outputs itself. So what do we want? We want a program Q, let's say. So a Turing machine Q. A Turing machine Q, which does the same thing as P of Q. Correct? So we want a Turing machine that when you execute it, what does it do? It prints itself. So in particular, it should do the same thing as P of Q, right? Because this prints Q. So we cannot just say, so we want this, essentially. We want M to be equal to P of M as a machine, but okay, this I don't really like the way I said that, so remove it. So what we'll do is we separate our Turing machine into two parts, A and B, which each of those will be a Turing machine. So the full Turing machine that we'll build will be the execution one after another of A, then B. Okay, and this will denote by AB. And here we just assume, you see it's a very light assumption, you can dismiss it very easily. But just to make things easier, we assume that the number of AB is just the number A followed by the number for B. So one idea to make a machine that prints itself, so we want this AB to print AB. We can just say, okay, for A, I will take this program. So when we run A, we will print B on the tape. Okay, good. And then we'll choose B to be P tilde of A. And what should B do? Well, running B after A will print the missing part in front. So it will print the A that we are missing. So A has the task of printing B, and B has the task of printing A. So this seems to work. But of course, we have cheated. Why did we cheat? Because we have a circular definition, right? So A equal P of B. So until now, there is no problem. We can define that. But now you cannot define B equal P of A, because A is defined as a function of B. So if you unfold this, you will have that B is P of B, and then B is P of P, and then you have, again, this blueprint of the blueprint of the blueprint, and so on. So let's try going around this. How do we go around this? So ultimately, what we want to do is really that. So we want A to print B and B to print A. So we need B to do the same thing as printing A, but without referring to A directly. Right? That's the problem because that gives us the circular definition. So what can B access about A without accessing directly? Well, what B can do is observe the tape and read out what's written on the tape after A has run, okay? So if A is equal the printer of B, what will be observed on the tape is itself, okay? So B knows about itself. But if B knows its own number B, that's all it needs to actually deduce what is the code for A. Because A is fully defined once you know B. Okay, so let me go over how this will be. So choose for B, we choose the following program. So when B gets M as input, it will read out what is M, okay, it takes it as input, and it computes the following Turing number, right? Well, it can do that, right? I mean, it's just computing a Turing number according to P. By universality, we can do this. Yeah, so here is just a comment. So we can compute the Turing number of P of M by universality, but it's not very clear here where it comes in, but it does. And then what B does after deducing this number, it just output this thing, and then it halts. Okay. So as you can see, B here is completely independent of A. It has some behavior on any Turing machine, on any input. And at the end, it prints this thing. But now, yeah, B is defined independently of A. So let's see now what happens when we choose A equal P of B. So you agree that we are allowed to do this because B is not defined as a function of A. So there is no circular definition. And here we have one. Okay, again, it's kind of a mindfuck the first times you read it. If you read it 2 or 3 times, you'll see that you will get it. So what happens? First, A runs. A is just P of B. So when A runs, it prints B on the tape and then halts. Okay. Then B kicks in. The first thing it does, it's look at the tape. Okay. Look at the tape, it sees M. In that case, M is equal to B. So it computes this Turing number here. But this just so happens to be the Turing number of A, because A is exactly P of B. And then B outputs this thing, which is just AB, and it is thus self-reproducing. Okay, so all we did as a summary is split our program into parts 1 and part 2. The goal of part 1 is to print part 2, and the goal of part 2 is to print part 1. You're not allowed to phrase it like this because it's a circular definition. So what happens in practice is that part 1 prints part 2. Part 2 look at the tape, deduces what is part 1, and then prints part 1. So this is a self-reproducing Turing machine. We have successfully constructed it, at least in principle. And we'll see that this thing of separating into 2 parts is crucial to writing quines. That we'll do next to kind of give you a practical implementation, maybe make it clearer. So are there any questions here? Again, if you're confused, it's perfectly normal, but if you if you have questions, let me know. Yes?
Maybe just a formalism, but the object which is reproducing itself is a Turing machine, which is like a composition of two Turing machines, first 9A and then B.
Right.
And unless you chose your Turing numbering in such a way that composition of Turing machines is concatenation
exactly.
of their code.
Yeah.
So you've done.
So exactly. So I assume this, just to make things simple, I assume that it is true that the Turing number of AB is Turing number A concatenated with B. Of course, you can change it. I mean, at this point of B, instead of outputting this, it can just compute the Turing number total. So it's not a big assumption, but indeed, you're right. Yes. Okay, so the side effect, just as a last note, the side effect of this Turing machine existing means that any Turing machine that you can think about is allowed to use its own Turing number. So here we've shown a machine. How can a machine come to know of its own Turing number? Well, you can input this procedure inside any Turing machine, and so any Turing machine can use its own number. That's just some kind of nice stuff. So it can, it can know about itself. Okay, so let's look at the interpretation of A and B, and you see that the magic kind of starts showing up. So this separation, as far as I know, this separation into two parts is kind of essential to the existence of self-reproduction. And how should we interpret these two parts? So the interpretation of A is that A is kind of the data. So A contains almost the full data that you need to describe AB. It contains B, but that's all it does, right? A is not a complex program. It just stores some data. That's it. And then B, on the other hand, he does a lot more stuff, right? It's just not a store for data. So B will call the code or the machine or the creature, whatever. And it is the actual part of the full living creature, which is AB, which actually does stuff. So the only job of A is to contain, or hard code, if you will, the description of B. And then the job of B is double. Okay. What B does is uses the data, so A, twice. That's extremely important, right? You really need to use the data twice. First, it uses the data to print the data. So it uses the data to print A. And then it also uses the data to print itself, right? It uses, or maybe it's also, in the way we've shown it, it's done in the other order. First, it uses the data to print itself, and then it uses the data itself to print the data, okay? And this is very important. So now, so this is the solution to the blueprint paradox. So if you recall, like every course, I mentioned this blueprint paradox. And the solution I mentioned before that is very simple. Just copy the machine and then just, instead of having a blueprint of the data, just copy paste the data. I mean, it's not that hard. And that's exactly what's happening in this machine, right? We use the data twice. We first use the data to copy the machine, which is the hard part. And then we use the data to copy the data. So it's just a copy paste. So that's how you solve the blueprint problem. And what's very interesting is that this is kind of screaming DNA, right? So you have A is the DNA, is some data, and this data somehow describes the actual living being that will be able to both copy itself along with the DNA, right? Or for a cell, the DNA contains the information to create a cell, and then the cell is able both to copy itself, so the cell part, but also to duplicate the DNA and then duplicate the data as well, right? So it's crazy that even in something as applied as biology, we see kind of the same ideas as you have in super abstract computer science about the existence of quines. And that's pretty remarkable, I think. So now let's go to the actual examples. So the first and simplest examples is the following in natural language. So we have this sentence here is a quine in the natural language. Why is that? Okay, so let's read it. So it gives us some instruction. Write the sentence in quotes twice. The first time without quotes. Okay, so let me follow the instructions of this thing. So I take the sentence in the quotes. I write it twice. So the first time without quotes and the second time with quotes. And as you see, the program self-reproduced, right? And even here, in this very simple example, we see this data code dichotomy, more or less. So the sentence in the quotes is the data, right? This just carries some data. And the sentence which is not in quotes here is actually the program. That's what tells you which steps to take to actually execute the program. And what does it do? So it instructs how to copy the data. And indeed, again, here we use the data twice. Okay, we first use the data to generate the code, and then we use the data itself to generate the data. right? So the data is used twice again. Again, this thing. Okay, any questions about this? All right, so what did I want to say here? Yeah, so here for this quine, it's kind of very abstract, but we also have some kind of this quine to work. It needs to run on a human, right? The human is kind of the substrate in which this machine runs. So that's why it's kind of not very nice. So now let's see how to do it in Python, and I think we'll close here if we have the time. So I will do this in Python because it's the language I know best, but I will try to not use the Python specific tricks. So you know that in Python you can do some very nice stuff like I have a variable, and then you can print the variable in the string if you put some brackets. I will try not to use all this fancy stuff, which means that my quine will be quite longer, but you will see that you kind of get convinced that you can do it in any language. Afterwards, if you look on the internet, you have quines which are just 2 lines in Python. So let's see how to do it. So let me give you kind of the idea of how we will do this. Let me zoom in a bit. The idea is very simple. We'll have a data variable here, right? This will hold the code for our program. And then we'll have some code here. And the job of the code will be to print the data, right? So let's start very simply. Okay. If I have this, okay, this program outputs nothing. Let me close this. But here now I can start. Okay, the data should contain the code, right? So I should put this here, right? So now if I run this, it prints print data. Okay, so I almost have a quine, right? I have printed this part. All I'm missing is the data part that I still need to print. Okay, and what we know is that we need to use the data to print the data. So kind of the idea will be the following. So first, I need to print this part here. So this part here is roughly data equal print data, right? But here I'm doing the wrong approach because I'm writing print data, and then when I go here and put it back into data, we run in this infinite blueprint. So here, instead of hard coding this value inside the print, I will just use the data to print the data. So I just use here. So for example, if I print here, if now I print that, I have that, which is the first line. Okay, that's good. We need also to print the second line. And the second line is, again, just print data, right? Because the data is supposed to contain our code. Well, I take my code and I put it back into data. And here we are almost done, but you'll see we have some problems that arise. Okay, first of all, we have these double brackets. For now, I cheat, and I will show you how to do it without cheating. So now let's come back to the beginning. So we have some data. The data contains this, which is that, right? Then what do? We use the data to print the data. So here we have printed this. And then we use the data again to print the code. So this thing should print this thing, right? So if I run this, you will see it's not quite. It's kind of similar. So you see we have data equal to this thing, which corresponds to that. And then we have print data equal data, which corresponds to that, then print data. So we are very close, but not quite, because we have this problem that this /n is not appearing here. It's interpreted as an enter. So, but this is a gist of it. I mean, this is the basic structure of a quine. The data that contains the code here, and then use the data twice. First to print this line, and then to print the rest. So now let's see how to do it properly without using different quotes, because other languages have no different quotes. So let's see. So the main problem is with the special characters, that sometimes it's a /n, and that's just text, and sometimes this means to skip a line. Okay, the main problem is the special characters. So what we will do is make a list of special characters and write them here literally. So the enter is /n, /n, yeah. Or wait, no. Here I want the real things. My bad.
No, backslash.
Backslash trick. I forget. Yeah, and the last thing that we want is the slash. Yeah. No, because here I want the yeah. Okay. That's fine. Okay, so we have no, because this should contain the actual. Wait, let me see on my cheat sheet here. Yeah, that's fine. Okay, my bad. All right, so here we store them into variables, so we'll see why, and then we'll make the first function. Okay. So this function will be kind of a building block to use this print function that we defined when we did the things. So this function will essentially do more or less what the Python print does, but it will allow us to replace some amount of variables. So we'll have a free variable. You will see directly what it does. And then we'll have the quotes. Okay, that Copilot is reading my other code and suggesting the answer. So the enters will use at, and then the let me think. Yeah, the slashes. Okay, so here what am I doing? So here I'm defining some aliases for the quote, the enter character, and the slash character. Okay, so these are just the ways that I can actually write /n and not be interpreted as enter. So what we'll do is just take the input string, okay, and I will just replace the aliases with their actual name. Okay, so here we replace all the quotes. Okay, so all these I don't know how to call this little hat will be replaced by an actual quote. Okay, then we will replace all the at by actual enters. And finally, we will replace all the slashes with an actual slash, or a backslash, sorry. Okay, and then we have these free variables. And what I will do is, okay, what I want to do with these free variables is just allow me to inject some arbitrary variable in a string using an alias, okay? So what I want to do essentially is this, right? So, okay, he's kind of cheating here. So I have an alias for the free variable 2. So what I will do is replace every occurrences of the string where I have f2 by the value free2. Okay, this allows me to replace anything I want in the string. And then I do the same with f1. There is just a minor problem which I didn't notice the first time I was writing I was practicing these quines, is that if you do this, you have a problem because free2 might itself contains some f1s. Okay, for example, if free2 is equal to f1, yes, f1, you have a problem because then you will replace also these by free1, which you don't want to do. You just want to replace f2 by an expression and f1 by another expression. Okay, so the way to do it is just say, okay, if we have a free2 that we want to replace, we replace all the occurrences of f2 by a unique token. Then if there is a free1 to replace, then we can go again freely and replace it. And then again, okay, this is not the best way to do it, but it's one way to do it. Okay, so all this does, sorry, all the following does is replace the occurrences of f1 by the string free1 and f2 by the string free2. Okay, so let's make some examples to make it clearer. Yes, and then we return the input string. So an example is I give, okay, string example. So if I am hello, this sentence is in quotes. So let me use single quotes here. So let's say I want to put a sentence in quote inside my string. I cannot do it because it will consider it as string quotes and then it will become crazy. So what I do, I use the alias of the quote, which is this one. Hello, I am in quotes. Okay? So then this is the alias we use for quotes as defined here. And now I can just do print, replace, string example. Whoops, my bad. String example. So what we'll do, we take this string, replace all the kind of special characters, special aliases. Here is just the quotes. And so if we print this thing, what we'll see is that it prints with the quotes. Okay. So all this trouble I have gone through is just to allow me to print the special characters. Again, if I want to print an enter here, if I want to put that enter, I just put this thing, which will be interpreted as enter. And now when we output, we have, we have a line break. What is it doing? We have a line break. Okay. And the last thing that I can do is, this is a special replacement, F1. Okay, so if I write F1 in a string, I can choose to replace it by whatever I want. I want to, let me write it replaced, right? So now when I call this replace function, it will figure out where the F1 is and replace it by that, right? So now if I run this, it has been replaced by whatever string I want. Okay, so that's the setup. And now we begin our journey to output our own code, which we won't have time to finish, but let me start you up. So we start defining the data. Okay, the data should contain the code, so we better put all this stuff inside some variable data. So we will have many variables data, but that's fine. So we have data 1. What should data 1 contain? It should contain exactly that. But of course, you have all the special characters that you need to kind of take care of. So what we'll do is just data 1 will be quote equal. And then the quotes here, I must use the special characters, the slash as well. Then at for the enter. Okay. Here again, the special slash, yeah. And then enter, then slash equal. And then double enter to go to the next one. Okay, so let's just see if I print data 1, what does it do? Okay, no, it's not good because I need to call replace on it to replace all the problematic characters. And now, good. Okay, as you can see, if I print replace data 1, we have just printed this part here. Okay. You might say, well, I could have done this much more easily, but you'll see that as we go along, we get better and better. Now, let me make a data 2 that we contain this full block here. Okay, so let me just put, for now, let me put it in triple quotes just for readability. And now you will see that we come on a second problem, and is that, okay, as we said, we need to replace all these special characters because they might bother us, and we can do that. But here we also want to print this, right? This one, we don't want to print it as a quote. This specific hat here should print it as a hat because it's a hat in the code. So we want to replace these ones, but not these ones. So that's kind of annoying, and that's why I put the aliases, they are free. So in this way, it's say, okay, for this round only, I will choose a different aliases for the quote. Okay, let's call it xq for x quote. So here, to mean that I want to put a quote, I will put xq. So it's kind of annoying, but thankfully I can just select all the quotes here. So all the quotes, the aliases for them will be xq. All right. Then we have another problem because this at here should not be an enter. It should remain as an at. And same for the slash. So here I need to choose another aliases for the enters. And so here I will choose xe, let's say. So let's put the enters. They should be, whoops. So let me just do this part and then I'll leave you go. And if you want to try to complete it, I will put it on the website. Okay, so all of these should be returns or enter. But I cannot use at because it's already used here. So I use another aliases, which will be xe. Okay, this will count as enter. Okay, perfect. So I think we're set up for this, and now we can just collapse it. So let's just check that it works. So if I want to print data 2, I now must be careful, right? Because I want the enters to be the XE, not the at. I want the quotes to be the XQ, so as not to clash with this one. And the slashes, okay, we don't have any slashes, but it should not be this one. What happens if I print that? And then, okay. Okay, we have double enters because I put them, but as you can see, we successfully output the function. And in particular, the big problem were these things. So these ones are correctly outputted, okay? Because we replaced XQ instead of the hats. So now let me just collapse so that I stop cheating with the Python special strings. So here we just remove all the enters, and then here we can use a normal quote. Okay, so we have this huge string, but in principle, when we print this huge string, it just prints for us this part of the code. This part of the code, okay? So now we are almost caught up, right? So this data 1 contains this part, this data 2 contains this part. Now we're gonna begin to use the data to print the data because we are kind of catching up. So I'm already 5 minutes over time, so we'll begin with that the next time. I'll put everything on the website, so keep an eye on the website the following days. And then we'll see how we can actually turn that into a quine, because right now we're just being outputting code, albeit in a very strange manner, but just outputting code. And the next time we'll see that with what we've learned, we'll catch up. We'll finish the proof of the quines, the abstract one, and then we are ready for actually looking at specific models. Okay, that's it. If you have any questions, you can come and ask me, no problem.